Now the mass moment of inertia of a disk or of a sphere, solid sphere. So for a solid sphere, suppose this is a sphere. These are the diametral axis, xx, this is yy, and this z will be like this. So this sphere is symmetric about all x, y and z axis. So now m is the total mass, of this sphere, and v is the volume, and this will be equal to 4 by 3 pi r cube, if r is the capital R is the radius. Now small m is mass upon volume, per unit volume, mass per unit volume. We have assumed that small m is mass per unit volume. Now in this sphere, consider a elemental disk like this at a distance x from here, and thickness of this disk is dx. Thickness of this disk is dx, and this is the radius capital R of the sphere, and this disk, for this disk, this is the small r. Radius of this disk is the small r, because when we cut down this sphere, there will be a disk like this along this axis. So xx is the rotational axis of this disk. Xx is the rotational axis of this disk. Now mass moment of inertia, mass moment of inertia of elemental disk, of this elemental disk about x-axis or rotational axis. So earlier we have find that for a disk about its rotational axis, mass moment of inertia is the mr square by 2. mr square by 2. So now here the mass of this elemental disk is dm. Mass of the elemental disk, mass of elemental disk is dm, and this will be equal to volume of the disk. Volume of the disk will be pi into small r square is the area multiplied by the thickness. This is the volume, pi into r square into dx is the thickness. And if this will be multiplied by small m, mass per unit volume, then it will give the mass of this elemental disk. So this is the dm is the mass of this elemental disk. So now for this mass moment of inertia of this disk is mr square by 2. So in place of mr, dm, and in place of r square there will be small r square. by 2. So this is the mass moment of inertia about rotational axis of this elemental disk. Now, if we integrate it between the limits from here to here, from here to here, so from here it is minus r, minus capital R, and from here it is plus capital R. So from minus capital R to plus capital R, if we integrate it, then it will give the total mass moment of inertia for this sphere about this x-axis, rotational axis. Now we put the value of dm in this. We put the value of dm. So value of dm is pi r square dx into m. So pi r square into dx into m and into r square divided by 2. This will be the value. Now this is minus r to plus r, minus r to plus r, and this pi multiplied by m, and this r square is r to the power 4 and divide by 2 and dx. Now this constant comes out, so pi into m divided by 2, or if we change the limit from 0 to r, then it will be twice here, and the limit will be changed from 0 to r, and r to the power 4 dx. Now this r to the power 4, find the value of this r. So for this r, if we find the relation in terms of x, then it will, this r square will be equal to this r square minus this x square. So from here it is small r square is equal to capital R square minus x square. This is small r square. So now put the value in this, pi into m divided by 2 into 2, limit 0 to r, and here in place of r to the power 4, put the value of r square as capital R square minus x square the whole square into dx. We have placed the value of r square as r square minus x square. So this will be r, this is r to the power 4, so this will be whole square. Now open this whole square, pi m, this 2 will cancel out this 2, so pi m 0 to r, and open this r to the power 4 minus plus x to the power 4 minus 2 into r square x square by expanding into dx. Now on integrating pi into m, on integrating r to the power 4 into x plus x to the power 5 divided by 5 minus 2 into r square into x cube divided by 3, and limit is 0 to r, and this will be equal to pi into m, and this is, put the limit x 0 to r at r, So this is r to the power 5 plus r to the power 5 upon 5 minus this 2 into r cube and r square, so r to the power 5 upon 3. This is, and when we solve this, this will come out as 8 by 15 r to the power 5. This will be the value. Now put the value of m. So value of m is total mass capital M upon total volume 4 by 3 pi r cube. This is the value of small m multiplied by 8 by 15 r to the power 5. Now when we solve it, this will come out as 2 by 5 capital M r square. So this will be as Ixx. Now this sphere is symmetric about all three axes, x, y and z axis. It is symmetric about all three axes. So Ixx will be equal to Iyy will be equal to Izz, and it is equal to 2 by 5 mr square. So this is the value of mass moment of inertia of a solid sphere about x, y and z axis. Okay, thank you. Now mass moment of inertia for a solid cylinder. So this is a solid cylinder of height capital H, and the radius of this base is capital R. So this is a solid cylinder. So total mass is capital M. Total mass is capital M, and volume of the cylinder will be pi r square H. So the mass per unit volume will be equal to m upon pi r square H. M upon pi r square H. Now to calculate the mass moment of inertia about this rotational axis yy, we will take a disk. In this cylinder, we will take a disk like this. So we have taken a disk, and this disk is of thickness dy at a distance y. So this is the disk. This disk is at a distance y of thickness dy, and the radius of this will also be equal to capital R. Radius of this disk is also capital R. Now this yy is the rotational axis of this disk. So mass moment of inertia of the elemental disk about yy axis or rotational axis. As earlier, this will be equal to mr square by 2. For a disk, it is mr square by 2. So now here the mass of the elemental disk is dm, Mass of the elemental disk is dm, and the radius of the disk is r. So this is mr square by 2. This is mr square by 2. So now dm for this disk, dm is equal to, calculate dm. So dm is equal to volume of the disk. So volume of the disk will be equal to pi r square is the area and dy is the thickness. So this is the volume of the disk multiplied by the mass per unit volume. Mass per unit volume. So this will be the mass of the disk, elemental disk. This disk. For this disk, this will be the mass of elemental disk. Now, if we integrate it, between the limits 0 to h, 0 to capital H, 0 to capital H, then it will give the total mass moment of inertia of the cylinder about y-y axis or rotational axis. Now put the value of dm into it. So 0 to capital H, and value of dm is from here pi r square into dy into m. This value is for dm, and r square, this r square divided by 2. Now this constant pi multiplied by m, and this capital R to the power 4 comes out and divided by 2, and the remaining is 0 to h, this is dy pi into r to the power 4 or m, and divided by 2. This will come out and 0 to h dy. So now this will be equal to pi into m into r to the power 4 into y to the power limits 0 to h, and this is divided by 2. So now I'm putting limits pi m r to the power 4 into h divided by 2. Now put the value of small m from here. So small m is capital M divided by pi r square h. So now here put the value of small m. So pi dot m, in place of m we put the value of small m, capital M divided by pi r square h. This is the value of capital M, and this is r to the power 4 into h, and this is divided by 2. So now this will be equal to pi will cancel out this pi, and this r square is cancel out this 2r square. So mr square by 2. H will cancel out this. So this will be mr square by 2. This is Iyy. So for a cylinder, about its axis of rotation, about its axis of rotation, the mass moment of inertia is similar to this. This is mr square by 2. Now mass moment of inertia of a solid cone about this y axis or rotational axis. So for this solid cone, the height of the cone is capital H, and this radius of the base is R, capital R. So M is the total mass of this cone and V is the volume. So volume, we know that 1 by 3 pi R square H. So this is the volume of the solid cone. Now small m is the mass per unit volume. Mass per unit volume. So this is equal to capital M divided by 1 by 3 pi R square H. So this is mass per unit volume. Now for this solid cone, we will take a disc, elemental disc like this, of thickness at a distance y, and thickness is dy. Thickness of this disc is dy, and the radius of this disc is small r. Radius of this disc is small r. Now the mass of elemental disc dm, mass of the elemental disc dm will be equal to volume of the disc. Volume of the disc means area of this disc is pi r square and multiplied by thickness dy. So this is the volume of the disc, pi into r square into dy. And if we multiply this by the mass per unit volume, small m, then it will give the total dm of the mass of the disc. Now mass moment of inertia of this disc about this rotational axis yy. So mass moment of inertia of disc about rotational axis or y-axis. This will be equal to mr square by 2. So this is dm into r square by 2. This will be the mass moment of inertia of the disc, mr square by 2. So m is the dm and r square by 2. This is the mass moment of inertia of the disc. Now for cone, this total cone, for this cone is integrated between the limits from here to here, because we will expand this disc from here to here. So this will be 0 to capital H, limits will be 0 to capital H, and this is dm r square by 2. Now to put the value of dm. So value of dm is this pi r square into dy into m. So pi r square dy into m. This is the value of dm into r square divided by 2. Now from this integration, we will take out the constants. So pi into m divided by 2. So pi into m divided by 2. comes out, and remaining is 0 to h, and this r to the power 4 into dy. Now this value of r to the power 4 by similar triangle method. So by similar triangle method, this is a here this is a smaller triangle and this whole is the bigger triangle. So by similar triangle method, this is r by y is equal to capital R by capital H by similar triangle method. So this is by symmetry, r by small y, r upon small y is equal to capital R upon H. Radius of the smaller triangle divided by height of the smaller triangle is equal to radius of the smaller bigger cone divided by height of the bigger cone. So this will give you r is equal to capital R upon capital H into y. So now put this value here. This will be equal to pi into m divided by 2, and this is 0 to h. And on putting this value, r to the power 4 upon h to the power 4 into y to the power 4 into dy. So now pi into m into r to the power 4 upon h to the power 4, and this will be the integration 0 to h y to the power 4 into dy. So on integrating, pi into m into r to the power 4 upon h to the power 4 into y to the power 5 upon 5, and these are the limits 0 to h. So on putting the limits, pi into m into r to the power 4 upon h to the power 4 into h to the power 5 upon 5. Now put the value of small m. So value of small m is capital M divided by 1 by 3 pi r square h into r to the power 4 upon h to the power 4 into h to the power 5 upon 5. So this h to the power 4 multiplied by h become h to the power 5, which will cancel out this h to the power 5, and this r square cancel this r to the power 4, and remaining will be r square, and 3 goes upside, and this 2 from here, this 2 and 2 divided by 2. So this 2 is with this, so this 5 into 2 will be equal to 10. So this will be equal to 3 by 10 m capital M, and pi cancel out, so this will remaining only r square. This is I/y about the rotational axis for a cone. So for a cone, the mass moment of inertia is this I/y is equal to 3 by 10 mr square about its rotational axis for a solid cone. Okay, thank you.